Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on applications of derivatives. The first application we'll look at involves cost. So we have a cost function here where C is the cost in dollars and X is the number of bottles of something that I produce. So hopefully you realize this is a parabola. So what we would get is a graph that looks like this. So this emulates a real life cost function. Because what would happen if you were making some items? So the cost of an item would start up higher. As you make more of it, the cost of producing each item decreases. But then we hit a minimum cost. This is the amount that you want to produce to reduce costs. And after this amount, the cost of producing each item goes up. So this could be, it's a strain on machinery. It stops working, or you have to hire more staff, or it's just you're not running efficiently or whatever. So that's why the cost function might look as it is. So let's say that we differentiate this. We get C dash is equal to, so we move the power to the front, decrease it by 1, so 0.01 times 2, decrease the power by 1, minus 2. So what this is the derivative of the cost function. This is the marginal cost. It allows us to calculate the cost of producing the X item. So for example, if X is equal to 200, then C dash, the derivative of the cost, is equal to 0.02 times 200 minus 2. And the answer we get there is actually 2. What this means is the cost of producing the 200th bottle is $2. This function here, if I substitute in X equals 200 into this one, it would tell us the cost of producing all 200 bottles. What would be the cost of all of those 200 bottles added up? But this one tells us the marginal cost. How much more money I would have to spend producing 200 bottles than producing 199 bottles. All right, let's now look at an application involving speed. So let's say the position of a particle is given by this function here. D is the distance in meters from where the particle started, and T the time in seconds. So we're saying this is only valid between 0 and 5 seconds. So let's calculate the derivative of this function. So differentiating term by term, that's the derivative of t cubed, the derivative of 4t squared, and the derivative of minus 3t. So this derivative here, this is the rate of change of distance with respect to time. It shows you how much distance is changing as time changes. This is therefore the velocity. This is the function that tells us the velocity. It doesn't have a lot of meaning by itself until we substitute some values for t. So for example, if I substitute t is equal to 1 into this equation, I get 3 times t squared minus 8 times t minus 3. So there I get minus 8 because d is in meters and t is in seconds. It's minus 8 meters per second. You can have a negative velocity, by the way. The negative just tells you it's going in the opposite direction at 8 meters per second. So if I were to substitute in here t equals 5, I would get 3 times t squared minus 8 times t minus 3. So the answer I get there is 32. So that means after 5 seconds, the particle is traveling at 32 meters per second. So we might be asked a question like this: at what times does the particle stop? So if it stops, the velocity is 0. It's not moving. But we just found out the velocity is 3t squared minus 8t minus 3. Whatever value we substitute for t in here, that tells you the velocity after t seconds. So if I want to find where that equals 0, I just need to solve this equation. So I'm going to use the AC method for factorization. So a times c, 3 times minus 3 is minus 9. So I find two numbers that multiply it to minus 9 and add to minus 8. So they're minus 9 and positive 1. So now I factorize in pairs. And now the common factor is what's in the brackets. So I have t minus 3, 3t plus 1. So solving these equations, I get t equals 3 or t equals minus a third. So that's when this function equals 0. So we don't really want to know about negative time, but we have a positive answer here, t equals 3. What that means is the particle stops after 3 seconds. It then restarts again, but it comes to rest after 3 seconds. So they're the kind of things we can do with derivatives. All right, thank you so much for tuning into this video. It's been the luckiest maths teacher in the world. Have a great day.